right at 10 o'clock now, so continuing the G2 instanton theme, then we're happy to have Jason Lotay going to talk about joint work with Gonzalo on deformed G2 instantons.
Yes, thank you very much, Mark. I will try to monitor the chat as we go along. If you have questions for me. Yes, I'm going to talk about deformed G2 instantons. So this is joint work with Gonzalo Oliveira. So what are deformed G2 instantons? So as the name suggests, these are special connections in 7 dimensions, which arise because they're in a sense mirror to certain calibrated cycles. So I'll explain what I mean by that in a little bit, but because of this interpretation in terms of calibrated cycles, one might guess there's some kind of enumerative theory underlying this. And another nice feature of deformed G2 instantons is that they have a variational characterization. They're critical points of a Chern-Simons type functional, which I'll call curly F. So these things, I didn't make them up. They've been around for more than 10 years. But interestingly, no one's actually bothered to try to find any, or maybe no one's thought of easy ways to find some. So what I'm going to describe is an elementary construction of the first non-trivial examples of these objects. And then I want to discuss some of the properties of these examples. So the first property is that the examples detect different G2 structures on the same space. So for example, they can detect the difference between G2 structures which are nearly parallel. So you can have 2 different nearly parallel G2 structures on the same space, but you get different answers for the number of deformed G2 instantons. And they can also detect between 2 different G2 structures that induce the same Riemannian metric. Another feature that we'll see is whenever you have sort of gauge theoretic objects like this, you're interested in the moduli space or the deformation theory. And what one finds by looking at these examples is obstructions to the deformations. And one sees some information about the topology of the moduli space of these examples. So finally, if I have some time, I will describe some relation to the Chern-Simons type functional and in our setting. So I will try to keep things elementary, but please do interrupt if you have any questions along the way. Okay, so let me start with the definition, like what is a deformed G2 instanton? So the setting that we have is a 7-manifold with a G2 structure defined by a 3-form, which is co-closed. And we're looking at connections, which I'm going to call A, on some bundle over this 7-manifold X. So I can remind you what the definition of a G2 instanton is. So one way to define a G2 instanton is to say that its curvature, which I'll denote by FA, satisfies the following equation. That if I take FA and wedge it with the star of phi, then I get 0. So that's a G2 instanton. So the definition of a deformed G2 instanton goes back to the work of Li and Leung. I should also have said at the beginning that these things have also appeared in the physics literature in some work on what's called open G2 strings, though I'm not qualified to talk about that. So because I'm going to say deformed G2 instanton a lot in this talk, I'm going to abbreviate that to DG2 for simplicity. And the equation is that you take your original G2 instanton equation and modify it by adding in this particular cubic term in the curvature. So this makes sense because, of course, this is a 2 form, so if you cube it, you get a 6 form, and this is a 6 form. So you can write this down. So of course, there are many things you could write down. Why would you write down this equation? So I find the argument from Lee and Jung is the following. So let's go just to Euclidean space, R7, and I'm going to split it as R3 plus R4.
Yeah. Thomas has a question about the meaning of f cubed if it's not abelian.
Yeah, well, I'm only going to care about the abelian case. Yeah, thanks, sorry. Yes, yeah, sorry about that. Yeah, I'm only caring about the abelian case. Exactly. Yeah, so we're looking at this R7 is R3 plus R4 with coordinates X on the 3 directions, R3 directions, and Y on the R4 directions. And then what we do is we consider U1 connect. Oh, sorry, and I'm going to take the standard G2 structure on R7. So just the standard flat one, Euclidean one. Then I want to explain this mirror calibrated cycles picture of Lee and Jung, which is to say, suppose we consider a U1 dg2 instanton, which depends only on the x variable, so only on the R3 directions. So here I'm using summation notation. And I ask, when is such a thing a dg2 instanton? And what Lee and Jung say is that's true if and only if, well, if I look at the components here, the u's, they give me a map from R3 to R4. So I can look at the graph of u, and I find that it's associative inside R7. And then what's true about the remaining piece, this piece, you can think of that as a connection on that associative, which has to be flat. So you have a pair of an associative graph and a flat connection. You can do the same thing if you have now only dependence on the y direction, so now only in R4. And now you can play a similar game with the v components here. So that's going to be a map from R4 to R3. So again, you can look at its graph. And, well, it's not going to be a shock to you what the answer is going to be. It's going to be co-associative now. And your remaining components is going to be an anti-self-dual connection. So now you have a pair of a co-associative graph and an anti-self-dual connection. Yes, and as I said, we're only going to be looking at U1 connections. There is a generalization, of course, with a different formula when it's not U1, but this is the case we're going to care about. If you want, you can make this more closely related to mirror symmetry by thinking about calibrated torus vibrations and the Fourier-Mackay transform, but I'm not going to talk about that. So what is the setting so what is it that you can do with these deformed G2 instantons? Like if you want to find examples, the sort of simplest thing you might try is to look at lower dimensions and look to see if it's got anything to do with gauge theories we already know about. So one thing you could do is reduce to 4 dimensions and suppose that your 7-manifold fibers over an ASD Einstein 4-dimensional space. And you could take some connection, U1 connection on Z, and then ask, when is its pullback a dg2 instanton? And if you set things up with the sort of standard G2 structure on X coming from various structures on Z, then you find that this is if and only if your connection is an ASD instanton on Z. But these examples are a bit fake because in this case, f cubed will be 0. So these are just G2 instantons. So we haven't really found anything new from this construction. A different case is when you reduce to 6 dimensions. So now we have our 7-manifold fibers over a Calabi-Yau 3-fold called Y. And suppose I have a connection on Y, and I take the Kähler form on Y, which I call little omega, and I ask, when is, same question, when is the pullback of this connection on Y a DG2 instanton on X? And what you find is that this is going to be true if and only if your B is what's called deformed Hermitian-Yang-Mills. So let me tell you or remind you what that means. That means that the 0,2 part of the curvature of B is 0. So that looks just like Hermitian-Yang-Mills. And the deformed bit is that you have a cubic expression that has to be 0. So the imaginary part of omega plus FB cubed is equal to 0. So these connections have received quite a bit of attention recently, particularly in the work of Collins, Jacob Yau, and many others. And there's a conjecture that the existence of these deformed Hermitian-Yang-Mills connections on a given bundle should be related to some kind of stability condition. And there has been some recent progress towards understanding this conjecture. Are there any questions at this point? No? Great. So I'd like to now describe the setting in which we want to do our construction, and that's going to be related to this 4-dimensional idea here. It's sort of orthogonal to that discussion there. So the setting that I want to think about is 3 Sasakian 7-manifolds. And so one way to think about 3 Sasakian 7-manifolds, these are a Riemannian 7-manifold, the metric which I'm going to call GTS for 3 Sasakian. And one way to say that is to say if I look at the cone on that space and look at the conical metric, then it's hyperkähler. So a nice fact about these guys is that there's infinitely many of them. So that gives us lots of places to look for examples of DG2 instantons. And 2 examples to keep in mind is, of course, the 7-sphere, just the standard round 7-sphere is an example. And a less trivial example is this Aleph-Wallach space is another example of such a thing. These 3 Sasakian 7-manifolds have a nice structure. So they're fibered over ASD Einstein. Well, typically it's a 4-orbifold. And the fibers are quotients of SU2. And this gives you a natural way to build G2 structures on your space X. So you have a nice coframe, which I'm going to call by eters on V. And I have some nice orthogonal self-dual 2 forms on Z with length 2. And with this data, I can build 2 1-parameter families of G2 3 forms for T positive. So I'm going to give you a nasty formula now. If people like formulas, it's not so important what the formula is, but there it is. One thing that you can check is that these phi t plus minus are all co-closed. But more important for us, well, that's obviously is important, but more important for us is that they induce a certain type of metric on our space. So the metric is t squared times a fixed metric on the fiber plus a fixed metric on the base. So that means we can interpret this parameter t as being the size of the fibers. And there's no typo here. This side does not depend on plus or minus. So whichever sign you pick here, you induce the same metric. And so what that says is that these are isometric structures. So they induce the same metric. So metrics like this, I mean, have been studied for a long time. I mean, there's work, it's in Bessie's book on Einstein manifolds. It's called the canonical variation. And you can ask, about Einstein metrics. When is this metric Einstein? And there are two possibilities. So there's two values of t for which this is true. The first is t equals 1. So if you take t equals 1 and you take the minus sign, you get a nearly parallel G2 structure, which induces the 3-Sasakian metric that we started with. If you don't know what nearly parallel means, it doesn't really matter. All that we need to know is that this is a special type of G2 structure which induces an Einstein metric. As I said, there's another value of t you can choose to get an Einstein metric, and that's 1/√5. So if you choose 1/√5 and the plus sign, you get a nearly parallel G2 structure, which induces another Einstein metric on this space, which is sometimes called a squashed Einstein metric, called it GNP. And this one is in some sense called strictly nearly parallel, because if you look at the cone on it, then it has holonomy equal to spin 7. Okay, so there's a lot of information on this slide. What the take-home message is that we have these two one-parameter families of G2 structures, depending on a parameter t, which is the size of this fiber. And we have these two distinguished G2 structures, which are nearly parallel, phi ts and phi np. So now it's very easy to write down the examples. So the examples come from the following very simple construction. So we take our 3-Sasakian 7-manifold with our G2 structures, and we just take a triple of numbers in R3, which I'll call A, and then I just write down this U1 connection. It's just basically one of the simplest things you can do. Write that down. It's defined on the trivial line bundle over our space. And I'm going to write R for the size of this A. So you can think of that as the distance to the trivial connection, because if I take A equals 0, I get the trivial connection. So I find the easiest way to describe our examples is through a picture. So as a result with Gonzalo. So we say that we find that A is a DG2 instanton on these spaces if and only if we have the following. So in the case of phi t plus, we find the following picture. So we always have the trivial DG2 instantons. That gives us a point in our space of solutions down at the bottom. That's when R equals 0. But then we have a family of DG2 instantons that's born at t equals 0. It's an S2 family that then lives until time is t is 1/√2, where it dies. So that's the behavior that we have for phi t plus. Whereas for phi t minus, instead of having just an S2 born, we have an S1 and 2 isolated points that are born, and there's a bifurcation, the S1 that lives forever, and these 2 points, which follow exactly the same path as the S2 did in the other case, and then die at that same time, 1/√2. So in particular, we can see what happens for our two nearly parallel guys. So for our phi ts, that's over here, we find an S1 family of non-trivial DG2 instantons. Whereas for phi np, we have an S2 family of DG2 instantons. And of course, the pictures for the two isometric families is rather different. Okay, any questions about that before I move on?
Would you expect that there are any examples on torsion-free G2 manifolds?
Right, so That's the million-dollar question. Yeah, exactly. I don't know. So that's, I mean, locally, yes, because that's, I mean, you have local examples that that were given by Li and Jung by the argument I gave at the beginning. But if it's compact, yeah, are there any that aren't G2 instantons? Even. Yeah, thanks.
What happens at the time when the blue branch disappears?
Yeah, that's a good question. So what happens at this time is that, well, there's nothing particularly special about the G2 structure that we can see, except that at this point, you find a family. So if you look for just G2 instantons on the trivial line bundle, then you won't find any except for the trivial one, except at this value. So at this value, you find a family of G2 instantons, so usual G2 instantons at this point, which is not, which are not DG2 instantons. That's something that I can say. Does that answer your question?
Yes, yes, that's.
Yeah, yeah, that's the only thing that I know about that point. So it's definitely special from the point of view of gauge theory, but I don't know how it links to this story exactly.
Jason, can I ask a question?
Please.
For the deformed G2 instanton that you've got, the instantons you've got on the nearly parallel guy,
Yep.
What do they pull back to on the spin 7 holonomy cone?
Right. So what they should give you is what would be, this is also in the work by Li and Jung, they define what are called deformed spin 7 instantons. Well, they don't call them that, but they should be called that. So they should pull back to one of those.
Okay, and have those things been studied separately?
No, I mean, that was going to be one of my questions at the end, was like, can you do the spin 7 version of this story?
Okay.
Yeah. Thanks.
I also ask a question.
Please.
So if I understand this correctly, this would be realized in terms of brains wrapping certain G2 manifold cycles they're in. Is it clear to you when you look at these equations, why the non-abelian case is more difficult? So we all know that, say, DBI actions, which characterize brain world volume effective actions, for non-abelian case are more complicated. So I was wondering, what do you know about the non-abelian situation? That's really the question. So when the connection is actually not a U1, but say an SU2 or U2.
Yeah, I mean, the answer is 0. We know nothing about the non-abelian case. But you can make sense of, I mean, it's not the same equation that I wrote down, but you can make sense of a non-abelian version of this. But we know actually, I think the amount that we know is 0.
Okay.
But it makes sense to think about it. I don't know what the interpretation would be.
Well, you would wrap multiple brains. So there's no obstruction, I think, to doing that. It's just, I think, studying that in terms of DBI actions, I don't know what the complication is. It seems you could write it down.
Yeah. I mean, it definitely. I mean, there's some work. I mean, there's abstract work done that makes sense for other gauge groups, but there's been no examples.
Okay, thanks.
Okay. Great. So I only have a minute left, but let me just briefly say something about the deformation theory then. So yes, so it's fairly clear if you think about this, then if you look at the non-trivial DG2 instantons we've constructed, at least when you know it's the nearly parallel G2 structure, then these are obstructed in terms of their deformation theory. So the moduli space has the wrong dimension. And perhaps unsurprisingly, the trivial DG2 instanton is unobstructed for those same nearly parallel G2 structures. But perhaps something that might surprise you, or it might not, depending on how you think about these things, the trivial DG2 instanton does become obstructed at exactly that magic value of t is 1 over root 2. So that value, the trivial instanton actually is obstructed. So where does this result come from? Well, it's work by Kawai and Yamamoto, who studied the deformation theory of DG2 instantons, and they said in the nearly parallel case, well, they showed in the nearly parallel case and in the torsion-free case, it's unobstructed if and only if it's rigid and isolated. So that sorts out everything apart from the t is 1 over root 2 situation. And there, what we find is that there is an infinitesimal deformation of the trivial DG2 instanton. There is one, but it can't be integrated. So it's obstructed. So it does not extend to a genuine deformation. And the way that we show that is by using the variational characterization of the of DG2 instantons. And the last thing I'll say is that a corollary of this is that you find that the moduli space of DG2 instantons, even on this trivial line bundle situation, contains at least 2 components of different dimensions. So this is what Simon mentioned yesterday could definitely happen in these theories, is that your moduli space has components of different dimensions. Okay, so I'm out of time. I don't have time to talk about the functional, but I'm willing to take questions if there are any. Thank you very much.
Let's thank Jason quickly. And then let's take maybe a couple of questions. Maybe Miriam has a question.
Yes, I hope I'm on the right track. You showed example of specific, simplest possible 3 Sasakian spaces that you're using. Of course, there is by now very rich explicit set of metrics of Einstein-Sasaki spaces, LPQR. Are there? Did you focus also on these generalizations and corresponding consequences for this more general Einstein-Sasaki spaces?
No, so well, what we do uses the 3 Sasakian. I mean, we definitely use that strongly. I mean, that's what we've used completely. I mean, what we were doing was just trying to look at the simplest situation where we could find non-trivial examples. I think the whole point of this story really is to open up the study to say, I think there's a lot more to explore in terms of these.
Right, the reason I'm saying that this other Einstein-Sasaki space is, I think in 7 dimension, they are of homogeneity 3, and those are very explicit metrics completely, analytically written. That matters, for drawing further hands-on conclusions on your studies.
The thing with that, Miriam, is that those are not tri-Sasakian, they're just Sasaki-Einstein.
Right, indeed, they are only Einstein-Sasaki, yeah.
Yeah, we use nothing about the explicit metric in any of this. This could have been any 3 Sasakian. So this was completely general. If you knew something more, then you might be able to say more. But this was supposed to just cover all of these at once. That was the idea.
So Yankee, did you have a question?
Yes. So I just want to ask the index of the linearization. What is the index
0.
of
0?
0. Okay, so it's self-adjoint, right? Formally self-adjoint.
Yeah, formally self-adjoint. Yeah, it forms part of, you can set it up as a self-adjoint thing.
I see. Thanks.
So Jason, the work in the deformed Hermitian-Yang-Mills, that is in the non-abelian case also, is that right?
Yes. Deformed Hermitian-Yang-Mills, yes, is also in the non-abelian case. So there is a question, someone wants me to show the functional, which I'm happy to do if we have time. Do we?
Maybe 30 seconds, so if you have the slide up, we can take a quick.
Yep. So that's the functional for you. So you do a Chern-Simons type thing, you pick a reference connection, You pick your connection, you draw a straight line between them on the product with an interval, compute the curvature, and then you take the integral of e to the curvature plus the dual of the G2 structure. So that's the functional. Great.
Okay, well, we're right at half an hour, so I propose if there are any further questions for Jason, we save them until the break at the end of these 3 talks. And let's thank Jason again.
Thank you.